Thank you for this introduction. Good morning, all of you. I think it is visible. The presentation is visible, I think, all of you.
Yeah, yes, sir, visible.
Okay, fine. So, my today's topic of discussion is role of feature extracting tools in image analysis. I will give an overview on different feature extracting tools uh, uh, can be used for many other applications like medical imaging or some other different fields, right? So as all of you are basically from whatever I have received different information from Professor Dinda, um, that most of you are in mechanical or material engineering background. So in my talk, I will mostly focus on image analysis part and then you can map those ideas in your site, in your working domain, in material engineering or mechanical. Okay, so in this topic, in this presentation, I may not give you that much practical understanding of material or mechanical engineering field, but I will give some ideas that may be applicable in your field. Okay, so let me start. Okay, so this is basically a era of artificial intelligence, and you have seen so many esteemed professors has given their lectures on different topics. And what are the? Let me first see what are the different domains where these AI and machine learning based techniques are becoming very promising applications. Okay, so first is that different pattern recognition application. Pattern recognition application means we have some specific image or specific type of image of different modalities. From that, we need to identify the pattern of an object or the different gesture of an object, right? Similarly, in case of computer vision, which is the basically a very vast area of AI and machine learning, in computer vision, we will work on the vision-based systems. It may be a remote sensing devices from the image collected from that. It may be a satellite image. It may be some other different modalities like thermal images. It may be from different other biomedical applications, right? So this computer vision is a very large domain of interest. Next is the very emerging topic of artificial intelligence is the robotics. In robotics, uh, the robotics actually the theme where we are actually replicating the human expertise or human knowledge to a robot. Now, that purpose of that particular robot, depending on the purpose of that work, the robot will uh, has to take different actions, has to do some specific jobs. Okay, to do those jobs, they need some specific informations, and how that information is being collected and those information being processed will help the robot to successfully execute that job. Okay, so such example I can give you one example that robotic one example is now the robotic surgery, right? Where in place of doctors, a robot is doing the surgery. He has to select the different instruments to put inside that human body to cut different regions. right? And also to identify that how that procedure should be follow a specific trajectory, and many other things are there. Fine. So similarly, some another aspects of this AI and ML are being used are the mm, condition monitoring of electrical systems. So electrical systems, different motors, different transformers are there. So in that case, this is a very it's basically a backbone of different industries. Now, what happens? There is a very, it is a very important to make a regular maintenance of those sections. In that case, if there is any fault occur, then this fault should be identified properly and should be taken care at a very within a very short duration of time, so that that problem can be solved efficiently, right? So this is the condition monitoring application of different electrical system that actually helps to reduce the human manpower to and to make a maintenance in scheduled way, right? Similarly, some very one of the most important topic of discussion right now is the natural language processing. In natural language processing, what we are trying to do, we can convert different languages in different other language. We can make the we can have an idea about the how we can convert the text into a speech signal or a speech to a text, right? So many complicated applications are there. One of them is the another aspect is the biomedical condition monitoring. The biomedical condition monitoring is nothing but related to the medical application. In medical applications, you can see that nowadays the doctors are becoming very dependent on different advanced techniques of signal acquisition or image acquisition. Those signals and images are being collected using different techniques like CT scan, MRI, ultrasonography, right? And in form of signals, we can have different sophisticated instruments for acquisition of ECG, brain signal like EEG, muscle signals from for to identify the strength of human muscle, that is EMG, electromyogram, like these things. Now, the problem, another question is that where we can have this AI application in medical. This here actually from those biomedical signal or images that has been acquired using different techniques can have different informations, clinical related information that may not be identifiable from any expert doctor, or sometimes we may not have availability of expert doctors in that particular region. So the general physician may not be that much expertise or equipped to identify those diseases accurately, right? So at the beginning stage, if we identify that whether this particular object has some properties of or some characteristics to be developed in a cancers, then we need to identify that. If we identify that at the very early stage, we can take different actions, necessary action, and we can prevent that patient or we can recover that patient from that particular disease, right? Now, the thing is that what I have discussed, those different applications, this pattern recognition, computer vision application, robotics, medical imaging, whatever, the fundamental thing is the signal or image processing. Now, whatever the different machine learning or deep learning based techniques you are you can see nowadays are emerging, all are basically depends on the signal or image processing algorithms. So how efficiently those signals and images are being analyzed. This slide is not changing. Okay, okay, okay. So the fundamental is the signal or image processing. That means how we can analyze the acquired signal or image. In the purpose of that analysis is to extract that information. We only need to process those information. How efficiently we can process, more efficiently we can achieve our goal. So this lecture, this particular talk will be more focused on fundamental image processing, signal processing, so that we can have an idea how those techniques can be used irrespective of different imaging modalities. We can use those techniques and we can have an access, or we can have a relevant amount of significant amount of informations we can extract from that signal or image, right? So the whatever the machine learning or deep learning based techniques are being developed, first and foremost thing is the applications of signal and image processing, development of signal or image processing algorithm to extract different informations. So first question should be, what is image processing? That means how what this processing means in case of an image. So as we know that nowadays the very efficient and very high quality image acquisition techniques are available. We can have a very good camera in our mobile also. So we can take a very high resolution images from our simple mobile. But and also some other imaging techniques are also available. From there we can have different representation of an object or our region of interest, right? Now from those modalities of images we have to identify that information. We need to it should be more clear about, we should be very it should be clear that all the information are very much accessible or very much clear to us, right? So this is an image, right? Now if we want to process that, we are actually making that image much more clear, or the information is being more clear to us, so that that quality of that image being improved, right? So in this way, when we can have a significant tool or efficient tool which can process that image, which have a proper informations in that image, that becomes a exact image which may tell you the all the information you need. Now from those specific image or specific properly acquired image, we can access, we can acquire different important informations, right? So what are the purpose of this image processing? So first is that image smoothing or image enhancement, right? So what we have done, we have seen that how an image can be more explainable, right? More we can have more proper visualization of that information. For that we need to improve the quality of image. We need to reduce the noise quantity of that image. We need to enhance some specific regions of that image. We may need to segregate or separate a specific object or specific region from that image, which is called image segmentation. We need to know that what are the different objects, multiple objects present in that image or not. If there is a multiple object having different features, having different colors, can be identified or can be segregated into different regions by using image clustering techniques, right? Next is the feature engineering. I am not discussing this. I will discuss in detail rather, right? Next, the compression. See, we have a very high quality image. We need to transmit that image some other other through internet or through some other way to some other place. So in that case, we may need to compress that image. We need by keeping in mind that we are not disturbing the quality of that image. So how efficiently we can compress that image so that its information is intact and can be transmitted within a very small size. Okay, that is the image compression. Similarly, image registration, pattern recognition, and the one application is biomedical systems, condition monitoring of biomedical systems, right? So these are the purpose of image processing. Now, what is a digital image? So a digital image is nothing but a two-dimensional signal. In that image, the fundamental element of an image is called the pixel, right? So a pixel actually depicts the intensity of that region in that particular location of that particular image. So in this particular image, if we consider a certain region, if we want to know what is the different intensities present in that particular region, we can have this sort of number of pixels present in that particular selected region and having different values of intensity, right? So basically, this collection of those intensities distributed along different spatial locations will construct an image. That means, in other way, we can say an image is nothing but a spatially oriented different informations within a specific region. So in that particular image, you can see that there is a circle which is white and its background is black. So what does it mean? If we make a 3D three-dimensional view of that, you can see that this particular region having a white or that higher pixel intensities, you can see we can differentiate that this region having a maximum intensity and the other regions has that intensity of 0. That means in this particular image, we have only two intensities, 1 and 0. Right? Similarly, if we have this sort of image where you can see the background is black and there is an object or a particular region which have different informations or different intensities, right? So how it looks like. So if we see that 3D view of that particular image, we can see that the background is 0. There is no information. There is a 0 information, and how the intensity of that particular image is varying in that particular image. So that's why I am displaying this having this type of representation so that we can have an understanding of that intensity, how this actually distributes. So these intensity are being distributed in different spatial location having different values, right? So if we want to represent an image, it is nothing but a two-dimensional matrix, right? A matrix basically having different spatial location, and at each location, the intensity of that location is nothing but that pixel location, and the intensity actually represents the what is the value or that what is the magnitude of that particular information in that particular location. So basically, we can present an image as a matrix in two ways, where the origin is represented 0, 0, or some other way it may be represented by 1, 1. So an M cross N matrix, this is nothing but an image having M cross N number of pixels. So, and each pixels have different intensity values, right? So if we have that matrix representation, this will be f of xy and cap f as this way regarding the, we can have the different locations, F00 starting location, then F01 as we execute one matrix. The same way we can represent that image in form of a matrix. So I have decided that let it be like that. When we are discussing on image processing, let us make some MATLAB or some tool-based technique. So it's where we can process that image, right? So in that from that understanding, and as your workshop is also on hands-on, so I have given some MATLAB-based techniques where we can have an hands-on experience of how to analyze an image. So first, obviously, we need to read that image. So you have a file. That file, if it is in your MATLAB directory path, then we can read that image by simply writing I equals to imread file name. If my file is in the same directory as the MATLAB directory. But if the source file in other directory, other locations, then we need to provide the entire path along with the file name. Now, how that file name actually we have to give? We need to say we have a file name as x.jpg, right? So the file name should contain the dot extension. That is either .jpg or some other extension, right? Now, when we read that image in MATLAB, that image is nothing but a matrix. If it is a two-dimensional image, it will be a two-dimensional matrix. If it is a color image, it will be a matrix of two-dimensional having three different layers, right? Now, if we want to display that image, we have read that image as F. Actually, it should be I. It should be I. F should be I. So we have an image I, and if we want to display that image, it will be in show I. Okay. Now, if we want to display multiple images, right? So in that case, for multiple images, we need to write figure, comma, in show F. That means if I have an image I1, I2, I3 like that, every time we need to write figure, comma, in show I1, I2, I3 like that. Fine. So we can have multiple display of images. So in MATLAB toolbox or MATLAB, you will see the image will be displayed in this way. Right? So in material engineering or mechanical aspect, if you have some specific problem where you need to acquire that image of that particular object and to identify different regions or to process that image, we first need to load that image or read that image to the MATLAB. Now let us come to the different types of images, right? So first is that color image. Color image has different representation. I have considered the RGB form. RGB full form is red, green, and blue. Right? So it is represented as M cross N cross 3. Right? So how it actually looks? It looks a red plane. It has a red plane, which is M cross N dimension. Another plane is the green and another is the blue. So it has three different planes having a dimension of M cross N, which has been shown here as 5 cross 5. Now, if this is a grayscale image, having its representation will be M cross N. So basically, this image will have an intensity which will be distributed from 0 to 255. Here, this is the representation of a 5 cross 5 grayscale image. Right? Now, that intensity is distributed from 0 to 255. Now, think in different way that if an RGB image has three different planes having red, green, and blue, and each of them have a m cross n dimension. That means each of plane is nothing but a grayscale in grayscale. So if we want to extract any of these RGB plane of that particular RGB image, our representation will nothing but a grayscale representation of that particular plane, whether it is a R, G, or B. Right? Next, similarly, a binary image. In binary image, it is also an M cross N image having only the intensity values of 0 and 1. So here we have seen that it is a 5 cross 5 image having the intensity only 0 and 1. Right? So we can convert an RGB image to grayscale image and a grayscale image to binary image. That means if we have that, either we can extract each of the plane of RGB image, that will be a grayscale representation, and also the entire RGB plane can be represented as a single grayscale image. And the most important thing is that if we convert this RGB image in a single grayscale representation, the information present in that will be different from each and every plane of the RGB image. That is either R, G, or B plane, which is nothing but a grayscale representation having different information. And if we convert the entire RGB image into a single grayscale image, then that image information will be different. So depending on different requirement, we can either convert that image into a grayscale image, or we can also extract different planes to extract different informations. And if we need to identify or need to separate if we need to identify or need to separate or segregate a specific object from that particular image, so that we can have only represented as two pixels 0 and 1. In that case, we need a binary image form representation where the region of interest or that object will be identified as 1 and background as 0. Okay, sorry. Now is it visible? I think
Yes,
it
sir.
is
Visible,
visible.
sir.
Okay, okay. Okay. So we have these three types of image representation. Now, how we can convert an image in different types. Right. So first is the RGB to gray conversion using MATLAB. The syntax is RGB to gray RGB. This RGB is nothing but my file, which is an RGB image that has been read using the imread command. Right. How this now here we are converting that entire RGB image in a single grayscale image. We are not extracting an individual plane. So how MATLAB convert that grayscale image into RGB form? They simply it is a weighted sum of all those different matrix R, G, and B having different coefficients which has been multiplied by each and every pixels of R, G, and B. Right? So first see, I have read that image, then in show will display that image in RGB form. IG equals to RGB to gray eye. That is how we have converted that RGB image to a grayscale image. And then again, we have displayed that image in grayscale, right? Next is the RGB to gray to binary image conversion, right? So that means we are converting that RGB image to a 0 to 255 scale, and then from 0 to 255 to 0 to 1 only. So what is that syntax? Syntax is in binarize grayscale image, comma, threshold. The threshold is between 0 to 1. So threshold nothing but a specific value within 0 to 1, which will convert that image, grayscale image, into binary image in such a way that if the values, the intensity values which are more than that threshold value will be converted to maximum intensity, that is 1, and less than that values will be considered as background or 0. So we have selected here that threshold value as 0.5, and in binarize IG, threshold will convert that grayscale image into a binary image IB. Or we can have another command, IM to BW, that is image that is in grayscale will be converted to a binary image using the same way by selecting a proper threshold value. Now the question is that if we have an image and having different number of pixels, each pixels have different intensities, represent different intensities, right? Now how those how we can know that what is the how that the information means that intensity values of that pixels are distributed in that particular image. So for that we need to know the histogram of that image, right? If we consider that image having different intensity values like 0, 1, 0.2, 0.7, 0.5. Now, if I want to draw the histogram, it will looks like that. What does it mean? What it depicts? It depicts that a specific intensity, how many times that intensity has been occurred in that particular region. That means here you can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 number of pixels having a maximum intensity 1. So you can see in the histogram the intensity 1 having a maximum height of 10. Similarly, some other intensities having different numbers which has been displayed. That means the histogram depicts the frequency of occurrence of intensity of an image. That is how many times the same intensity has been occurred in that particular in that particular image or that particular region. So that means from histogram we can have a distribution of that particular information present in that image. So how we can display that histogram? Just to write ImHist I. So this ImHist I will show you the intensity distribution of an image. It is not the same image I am showing here. This is from different image, but you can see that the x-axis is nothing but the intensity from 0 to 255, and the y-axis is the number of beams, that number of times that particular intensity occurred in that particular image, right? So this is image histogram. Now image enhancement. So enhancement means we want to improve the quality of that image, or we have some other objective like we want to increase the intensity of a specific region of an image, right? So if we consider this an image, right, don't go for that modality or type of that image. You can replace that image by simply any other image of any materials or any other mechanical things whose characteristics you want to study using image processing. Now see what we have done. You can see that the difference between the left hand side image and that right hand side image. The difference is that we have enhanced a specific region of intensity at a very high value and other intensity values at a very low value. That means we are trying to make that enhancement in such a way that some regions will be more brighter and some region will be more darker. So how? In MATLAB, if we write in adjust, right, I 0.2 to 0.4, 1, 0. That means the intensity values between 0.2 to 0.4 will be in between 0 to 1. Other values except that 0.2 to 0.4 will be converted in either 0 or 1. That means the values below 0.2 will be more darker and the values more than 0.4 will be more brighter. That is has been achieved here. In similar way, if we change it that 0.6 to 0.8, within that values will be in between 0 to 1, that is in the gray region, and the values which is more than 0.8 will be more brighter and the 0.6 less than 0.6 values will be more darker. Then we will see this sort of enhancement. You see in the original image we have different gray regions, and in the next one we have still some gray regions, but in the last one, the gray regions in the middle of that image, middle of that region has almost removed. Right? So in this way, we can manipulate or we can play with that intensities in that particular image. Next is the linear spatial filtering. So what is that filtering means? This is nothing but filtered is nothing but to allow some information to pass and block others. That means we are interested to some information, some intensities, and not interested to other informations. So we will not consider those. We will only focus on those informations which are we are interested, right? So first is the one of the most important spatial filtering is the convolution. So what it does mean? So convolution is nothing but the interaction between an image and a small object or usually called a kernel. So in convolution, we have a larger image and a very smaller kernel which will interact with that image and try to extract different information present in that image, which is depends on the properties or the characteristics or the distribution of values in the kernel. So let us see. So if we consider this as an image M cross N, and we have a small kernel which have this distribution, okay, K cross L size, which is less than M cross N. Now, if we want to perform the convolution operation of these two, that means this kernel will explore this image to identify different information from that particular image. So first it will be placed here. Then what will happen? The weighted sum will be calculated. That means the values present here is the 1, 2, 1, 0, 0, 1, 1, 2, 3. And if we place that kernel here, then each of the pixel intensity corresponding to that particular value of the kernel will be multiplied and overall sum will be replaced by the center pixel, right? So if we move these pixels, this kernel one location in the right side, then again this value will change. In the same way, if we want to move in the whole image, we will get a certain representation of that image. Now here it was m cross n size of image. Now we are getting m minus k plus 1 cross n minus l plus 1 image, having different information. So what is the problem associated here? Problem associated here is that when we are moving this kernel one by one, we are actually making the weighted sum of that and replacing the center pixel, and our image size has been reduced. Right? Now, if we want to know the what is actually we are losing the information present in the farthest corner of that particular image. That is the first row, then the last column, then the last row, first column. Right? So these informations we are actually losing. So to make that make sure that these informations are also being present in the output convolved image, we need another technique that is called zero padding. What we will do, we will pad a zero outside that image so that the previous image size, which now is now become m minus k plus 1 cross n minus l plus 1. Now if we do the same operation of placing that particular kernel at different locations, you see we are actually considering all the farthest cornered information of that image when we move that kernel at every location, and we will get Okay. Am I audible? Am I audible and my presentation is visible? Can you please confirm?
Sir, can you tell one?
Is it visible?
Sir, can you? Yes, yes, sir. It is visible, and also, sir, you are audible, sir. Also,
Slide is changing, right?
sir. Yeah, yeah. Slide is changing now, sir. Slide number is 16.
Okay, okay.
Yeah.
Okay, fine. Okay, sorry for the inconvenience. Let us start again. So we were discussing about the spatial filtering. That means I wanted to focus that if we have a specific kernel, which is nothing but the representation of a filter, it may be that filter means that the combination of different pixels of that particular kernel or the different values of that matrix of that kernel is defined as a filter. If that filter is explore that entire image, then depending on that combination of that values, it will extract different information from that particular image. So we have discussed that if my filter is a Gaussian, if my filter is a Gaussian filter, then when I am placing my filter in this particular region, this filter will try to extract the relation between the center pixel and its neighboring pixel. When it will be placed some other place, in same way, it will try to identify the relation between center pixel and its neighbors with respect to the combination of the values present in the kernel. Okay. So this is how we can make different averaging filter. We have discussed the averaging filter. Now we see the same way in the averaging filter, what we are trying to do, we are trying to averaging. That means we are trying to make that particular region more smooth. Following smooth, why it is more smooth? Because if we have a different intensity variation and we are making an average of that particular region, that means all the pixels which have high or low value, that will be in the same value, right? So that averaging will nothing but making that image a smoothing, right? Now, this all is what we were in the spatial domain, right? In the we are only having that concerned about the spatial information present in that image. Now let us discuss about the frequency domain information. So if we want to know the frequency information of an image, we need to perform the 2D discrete Fourier transform. So Fourier transform will give us the intensity distribution of that particular image at different frequency information or different frequency location, right? Now, if we consider this as an image and its frequency spectrum will look like this, that means the high frequency present is represented that the highly intense region at the center, and then it has been distributed throughout that particular image. That means how that intensity of that image is being distributed in different frequencies, right? If now let us adjust that image intensity. What we have done, we have made some region of image more brighter and some region are more darker, right? So if we see the Fourier spectrum, then we can have a significant difference. Now see, previously there is a single dot, high intensity dot at the center, and it has gradually distributed in the other locations, right, in along horizontally and vertically. Now you can see this image in the Fourier spectrum of that image after adjustment. You can see now the brighter region are more centralized, more in center. The brighter region are more, and then you can see there is a very not non-uniform in distribution of that information in the frequency domain. So that means the significant number of image information are adjusted. That means having a high intensity value, and the remaining information are basically the low intensity value. So there is a no smooth transition between the different information and according to different frequencies. Now the question is how we can understand what is the frequency of an image. The frequency of an image is nothing but how the intensity of an image is distributed. If the region having the same intensity, this is basically a having a smooth region, or having a very smooth same intensity values, it is basically a low frequency region. If there is a significant distinct changes in the intensity, then we can have a very high frequency information can be present. So in that image you can see the one is very high intensity and other pixels have a very low intensity. So there is a significant intensity difference between those two. That's why we are getting a very high frequency information, more high frequency information in the adjusted image than the original grayscale image. So this is the Fourier spectrum region for that original image, and here you can see that the difference between these two, how that region has been changed. The center region of the Fourier spectrum has been changed. So if this is an image and if we have the spectrum boundary, then the spectrum or the Fourier or the frequency information of that image has been distributed along that particular region and having different boundaries, which depicts that different frequency informations present in that particular image. So that also gives us another specific information which is not accessible in the spatial domain. Now let us see, this is an image and it is its Fourier spectrum. Right. Now what we have done, we have selected a specific region of the Fourier spectrum and we have eliminated other frequency information from that particular image. So how that modification will be reflected in that image, you can see that image has become more blurred. Right. In the same way, if these two images, one is the Einstein and another that lady, these images having two different intensity, then if we merge those two images having different frequency information, we will see this sort of image. That means in that particular image, the dominant portion is being the intensity distribution obtained from the Einstein image than this particular lady. So that why? Because you see in the Einstein image, we have made some adjustment and make some significant intensity difference between the facial information and the background information. Whereas in the image of this particular lady, she has almost uniform distribution of that intensity. So if we merge these two images, it will looks like that, where the high frequency information of the Einstein image will be predominated. Right. In the other way, we can say if there is such an image which has a multiple frequency components, and if we can extract those frequency components and reconstruct that, then we can have different informations we can extract from that image. Right. Now let us come to a very specific tool that is called the mathematical morphology. So this is a mathematical tool that actually deals with the morphology or the structure or the shape of an object, which may be very helpful for different mechanical or materials engineers applications. So mathematical morphology is a theory that works on the spatial information only. So it basically try to identify, or it depends on the spatial, structural, or that particular shape of different objects. Fine. So the basic element of the mathematical morphology is a structuring element. It's called a structuring element. So structuring element is the fundamental element of mathematical morphology. As we have discussed in the filtering stage, the kernel is the filter that actually have different characteristics, and because of that characteristics, we can extract different information from that image. Similarly, here the structuring element is nothing but a filter which will deals with the structural properties of different objects present in that image. Right. So these are some mathematical things. Now, what is the structuring element? Structuring element is nothing but a smaller image compared to the original image, having different shape and size. We are emphasizing the terms shape and size because we need to assess, we need to focus on the different morphological properties of the objects. So when we are concerned about the morphological properties, so the filter should be able to extract those information, right? So the filter have different shapes. It may be a square, it may be a diamond, it may be a linear shape, it may be a circle, different shapes, and also different size. That means if we have a very small object to identify, to extract, then my kernel or that structuring element size should be small. If the object is having a shape almost similar to an circle or an ellipse, then my structuring element should be selected in the same way. That means in case of mathematical morphology, there is no predefined rule for the selection of the structuring element, that is its shape and size, selection of the shape and size of the structuring element. So we have to select a proper shape and size of the structuring element depending on the objects present in that particular image. So there are different operations we can perform in mathematical morphology, and those operations will give us different information. The basic operations are the erosion and dilation. So erosion means it will erode that image, and dilation means it will dilate that image, right? So what will happen? The interaction between the original image and the smaller structuring element will be such a way that it will take the minimum values to erode that image, and also in dilation, the structuring element will interact with the original image in such a way that it will dilate or take the maximum operation of that particular region. So if this is an input image, if this is my structuring element, so after erosion, the image will look like this. Now see, this structuring element is eroding or that interacting with that input image and try to preserve the size and try to preserve the shape of that object of interest and try to extract different regions according to the shape of the structuring element. Now, if we dilate that image, that means that image has been dilated, it has been expanded throughout its boundary by means of applying the dilation operation with the same structuring element. Now, how it works? So dilation actually means the heat operation. Heat operation means, see, this is my original image. The red color pixels are my object of interest, and this is my structuring element, right? So if we consider the red color as 1 and this white as 0, then for the structuring element, all pixels are 1, right? Now, in case of mathematical morphology, what we have to do, we need to place the structuring element at different region. Now, the question is that in the dilation, if the structuring element, when we are placing that structuring element in that region, whether any of that pixel is coinciding with the object of interest or not. If any of the pixel is coinciding with the object of interest, then we have to replace the center pixel with the maximum value within that neighboring objects, neighboring pixels. That means when this structuring element is being placed here and it has been a coincide with that object of interest, so among these 9 pixels we have to take the maximum and to replace the center pixel location as this. Similarly, if we move this structuring element here, we can see that now 2 pixels are coinciding with the object of interest. We have replaced the center pixel. In the same way, if we move, the same thing will happen. In this way, if we move the structuring element through the entire image, we will get a dilated image of the original image. So dilation is all about the heat operation. Similarly, for erosion, what happens if we place the structuring element, if that structuring element fully contained by the object of interest or not. So if we place the structuring element here, the structuring element is not fully contained by that object or region of interest, or it is not fully fit within the object. So if it is not, then we can't replace the center pixel with the minimum value of that particular neighboring pixels, right? So there is no values has been changed in the eroded image. So like this, if we move that structuring element, we can see that it is not being fully contained by the object. Now, if I place the structuring element here, when it will move the different ways, different sliding one by one, and when it will place in that particular region, we can see that the structuring element is fully contained by the object, and that's why the center pixel will be replaced. In the same way, if we place here, the center pixel should be replaced. So when that structuring element is fully contained by the region of interest, we can replace the center pixel. So now this is the eroded image of that original image. So see the difference between dilation and erosion. So these are some mathematical properties of those operations. Now, as these two are the fundamental operations of mathematical morphology, the combination of these two makes the other operations like opening and closing. What is that? The erosion followed by dilation is the opening, and dilation followed by erosion is the closing operation, right? So what happens? Why it is necessary? You see that if we try to extract some specific object from an image, or based on that intensity distribution of that particular object, we need this opening and closing operation. See these figures that has been shown. This is the input image. This is the black portion is my region of interest, right? And we have a structuring element. Now see how this structuring element has been extracted, that is opening different regions having the same structure or same shape of that structuring element. We can see that how it has been extracted. And similarly, if we want to make the closing operation, then what it will do? It will work on the border region, and it will make some similar intensity values, same values, and then what will happen? The basic structure will be same, but there will be some difference in the structure because of that closing operation. So these particular operations will give you to identify or to extract different objects having the same structural property as the structuring element. Now, by using this erosion and dilation, opening and closing, we can design different type of filters. One of such filter is called the morphological gradient operation, and this operation is actually called the gradient operation. And because of this, we can have different filters. So you see, the dilation operation expand that object boundaries, and erosion actually eroded that region. So if we subtract this dilated image from the eroded image, then we can have a border region where the intensity difference is maximum. Right? Like this way, we can design different filters. Let us see how we can use this particular technique to segregate or segment a specific region and identify the border. So if this is my input image, which is in RGB form, we make it converted into grayscale. Then we perform a morphological closing operation on that image by a circular structuring element, right? Why we have to consider this circular structuring element? Because in most of that problem, most of the images are almost ellipse or circular in nature, right? So now see, if we perform the closing operation, what will happen? The intensity distribution of that particular region or that particular object of interest has been changed based on the distribution of intensity present in the original image within that region, which has been coincide with that circular kernel or circular structuring element. Now what we have done, we have subtracted the closed image from the complement of the grayscale image. And what we have obtained, we obtain a distinct intensity difference between the region of interest and the background. So in that case, what we want to do, we want to segment or segregate the region of interest. So now, if we have a distinct difference between the intensities, we can select the proper threshold and we can segment that region of interest. Right. So now, after segmenting that region of interest, we have to identify the border region, right? So what happens? We have eroded that image. Now you see, because of erosion, the border region of that image has been changed. So after erosion, again, a morphological gradient operation has been performed by subtracting the eroded image from the segmented image, right? So if we subtract, we can get the single pixel border of that particular region of interest, right? So in this way, depending on different problems, having different images of having different informations, different objects, shape, we can extract those shape, we can segment those regions using this mathematical morphology by making different filters, right? So these are some examples. So now after this is not actually that much necessary. That is how we can quantify how properly we have segmented that region. That are the different quantification techniques. Now let us move up to the MATLAB part, the coding part, how we can develop such thing. So threshold value, how we can determine from a grayscale image, the threshold value can be determined by the syntax gray thresh and that grayscale image. We can have the threshold value. And from that, applying that threshold value, we can use the imbinarized or IM to BW threshold to get the segmented image. Now, how the morphological operations can be performed? For the morphological operation performance, for the erosion, we have a syntax of im-erode, I-M-E-R-O-D-E, IM, AC. IM is my image and AC is the structuring element. Now, to define the structuring element, that is, we need to take different shape and size of the structuring element. So, to define the structuring element, the syntax is strel shape param. Param means the parameters associated with that particular structuring element. So it may be radius, it may be the length, it may be some orientation we can define, and accordingly that the different structuring element will be formed and the erosion operation can be performed. Here we have seen, I have show that how a circular structuring element can be constructed, and that structuring element will be used for erosion operations. We can see that for different shape and different size, actually for different size of the structuring element, how the intensity distribution of that image has been varied as from the original image, right? Similarly, for dilation, the syntax is I am dilate in comma AC, where in is the image and AC is the structuring element. And here we have seen that how different size of the structuring elements can change the intensity distribution in that particular image. So that means from the after operating on the dilation operation on that image, if we can design a proper filter, morphological filter, then we can extract different objects having the same size or shape of that particular structuring element. So this is the morphological opening. For opening, we have also the same syntax, I am open. And for closing, it is I am closed. The structuring element will be defined as I have shown you previously. Okay, fine. So I am just at the end of my talk almost. So these are the operations. These are the different techniques we can use to identify different objects. Now let us take an example. See, if you have have a mechanical system or it may be some steel we have produced, right? Now we want to know if there is any crack present or not. So the crack may be a hair-like structures. So from that image, we can identify whether there is any crack or not using morphological techniques. Similarly, if we want to assess the quality of that particular material by if the smoothness or surface of that material can be helpful to identify the quality of that particular material or any other property of the material, then in that case we can use different filtering technique so that different structures, different different features from that particular information can be from that image can be extracted. Now, can we tell me who is this personality? Anyone? Anyone? Can you please respond? Okay, okay. So this is the personality. This is a cartoon figure of Mahendra Singh Dhoni. Similarly, this is a cartoon figure of Rajinikanth. This is the cartoon figure of a Bill Clinton, right? So how we can identify these personalities from these cartoon figures? Actually, we are trying to find out the similarity between the actual figure and these cartoon objects, right? So when we can find out the most similarity, we can identify that person. If we don't able to find, then we can't identify. So this information which we are searching for to make an inline with that original image, original personality, and that cartoon figure is nothing but the features. So feature is the feature, and we have to do the feature engineering to extract those information to identify or to detect different particular object. Fine. So what are the different features? From the morphological operations, if we can identify or we can segregate a particular region, we can have a lots of features, lot of information from that image. That area, perimeter, maximum major axis length, minor axis length. What is that? This actually describes the morphological property of that segmented image. How that segmented image looks like. We are actually quantifying those particular information, right? Similarly, after identifying that border, we can determine how that border characteristics is. whether the border is a smooth or it is a very irregular shape. Now you see that a smooth or irregularity, it is a very subjective matter or subjective quantity. So can we quantify that? How irregular it is? So for quantification, we can have different tools like fractal dimension estimation. That fractal dimension estimation will give you the fractional dimension of that particular object or that particular figure, that can give you an idea about the irregularity present in that particular region, right? So from that also you can use for the texture feature extraction, that is the how the texture of that particular object is distributed, whether it is a smooth or whether there is some irregularity. So for that we can have different techniques like fractal based regional texture analysis. That means we first have to identify different regions having different textural information. That means different intensity variations. And from that, we can identify how that intensity has been distributed. If it is a regular pattern, then it is different. If it is an irregular pattern, then we can use the fractal estimation so that we can identify how irregularly that intensity are distributed within that region. Similarly, another tool is called the wavelength transform. In Fourier transform, we get the frequency information. That is, which frequency is present in that particular image and how that frequency information is distributed. But we do not have any access regarding the spatial location of that frequency information. That means which frequency information at which spatial location has been occurred, we can't determine from Fourier transform. For that, we need a time frequency domain analysis, or we can say a spatial spectral analysis. So in spatial spectral analysis, we can have this wavelength transform is a very efficient tool which can give you not only the frequency information but also in which location that frequency information present. So from that we can also have an idea about that frequency distribution. Here we can see that the high frequency will be present at the border region where the maximum intensity variation is there. So you can see this image, this particular image, where we can have the very high magnitude values present in the border region, right? Whereas the left-hand side image gives you the intensity variations along that particular region of interest, right? So we can also have some other information that is whether there is any high frequency information present in that specific region or region of interest or not. So in this way, we can have different spatial spectral information of that representation of that image, and from that we can have different informations. Similarly, another very important feature extracting tool is the cross correlation. That means if we have an image and we have some other images looking same type of that, or we want to identify a specific information or specific type from that particular image which is already defined. So what we can do, if we have that particular information, we can find the correlation between that input image with that particular smaller object or the small image, right? That means we will try to identify the similarity between my selected object or selected small image and that original image, right? So it will give us an idea about where that image similarities are present. So if we do the cross correlation, and that cross correlation will give us another matrix which is called the cross correlogram. From the cross correlogram, we can identify which region have the maximum similarity with that object or the small image, right? And how we can define that similarity? We have different correlation coefficient. So highest correlation is 1, and gradually it will decrease. So from this figure, we can see that these having a value of 0.9, 0.886, 0.89, these regions having the maximum similarity with the original image and the kernels. That means we have that original image. Here we can see these are the original image and these are the kernels. So we are trying to find out whether these kernel properties having the similarity in that particular image or not. So if there is the similarity, then the correlation coefficient value will change, and from that we can identify that these regions have the similar properties as my selected kernels, and from that similar regions we can have extract different features or different informations, right? So similarly, the cross spectrum, the Fourier transform of this is the cross correlograms, right? So if we take the Fourier transform of that cross correlogram, we can get the cross spectrum. That means the frequency domain information. It depicts that whether there it depicts the spatial information similarity. The cross spectrum depicts the frequency domain similarity. That whether there is any similarity between the kernel and the original image in which frequency location. You see that here the higher value depicts the higher similarity within that frequency region, right? So, and in this case, you can see that there is some frequency that is similarity in that region of frequency and in the other frequency regions also. So in this way, we can also get some frequency information, which is the similarity based frequency information. And from that, we can also extract different features. Right. So why we are actually extracting those features, as I have told at the beginning, that how efficiently we are extracting different information. These information will able to identify that object or differentiate between two different objects or multiple objects, right? So we need to extract the proper features or proper information from that image using an efficient feature extracting tool. Now the problem is that when we extract those features, we may have a large number of features. Now when there is a large number of features, then obviously there will be some correlation between those features, or the same features may be extracted multiple times, right? So it will not improve the identification performance, which we usually do using different machine learning techniques. So for that, we need to select the features. Select means we need to select those features which able to differentiate the two objects with highest amount of dissimilarity, right? So for that, there is a technique called recursive feature elimination based feature selection technique. Then shortly it is called SVM RFE. So we have used different feature extracting tools and have extracted n number of features from those images, right? Now, from those features has been given to the classifier. Classifier is nothing but a tool which identify or differentiate different properties or different classes, right? So this classifier will be given those features, and based on those features, the classifier will assign a weight value to each of those features from feature 1 to feature n, right? Now from that, as we want to select those features which are very important. So what we'll do in the next iteration, the half of those features will be eliminated, right? And remaining feature will be again used to classify that SVM classifier, right? So every time we are eliminating half of those features and using remaining half for the classification. In this way, we can now select a threshold value for which we can have a specific number of features, and using that features we can classify and improve our results. But the problem is that when we are eliminating the half of those features, we may eliminate some important features, right? So here comes another technique called SVM RFE with correlation bias reduction. That means we should not, we should aware of that we are not eliminating the that important features. Why? Because it has some correlation with some other features, right? So let us reduce that bias. So what happens again, that feature will be fed to that classifier. It will give allot different weight value depending on their weightage. That means how important that features. Based on that, they assign different weight value, and they have been arranged in a different orders from F1 to Fnth. Now these features, after eliminating the half of those, that feature will be differentiated in two sectors. One is the existing features, another is the eliminated feature. Now in the eliminated feature, we have to identify which feature is still important and that can be used for the next time of classification. So what we do, we select two threshold value. One is called group threshold value, another is called the correlation threshold value. The correlation threshold, the group threshold value, what it does, it from this eliminated feature set, it select a group of features based on the correlation threshold value selected. So from that, what it will do, from the selected group, the feature which has the maximum correlation with that group members will be moved back to the existing feature set, and this new feature set will then be used for the classification. In this way, what we will do, we can again reassign the eliminated feature which may be a important feature, and we can improve the classification performance. That means we can improve the identification performance. So after using different feature extracting tool according to our requirement, it may be different for different imaging modalities. We can extract different features. That means it may be a morphological feature, it may be a Fourier domain, that is in frequency domain information, whatever. This feature set, from that feature set, we need to identify the most important features. Then, if we can identify the most important features, then only we can improve the performance of the machine learning algorithms. Now come to the recent trends of deep learning based techniques. The deep learning based techniques, what it does, whatever we have discussed, these techniques, they are trying to incorporate in a model where those features will be extracted automatically, and at the end, again, they will do some techniques through which they are actually identifying the most important features and then use the classification technique to identify that objects. So this is the fundamental idea of the image processing and signal processing, which can be used in the deep learning based techniques, and then you can use different modalities of images according to your applications. So these are some references, and I should acknowledge some my collaborators. And these books I have published, you can get this book from Amazon and some other such purchasing medium, right? Okay. So thank you from my side.
This is details of such.
Thank you, sir, for your nice presentation. Due to lack of time, this is the detail of speaker. You may contact him further. Then the next session is for at 2 o'clock or 2 p.m.
Thanks.